Hi guys, welcome back to the Online Student. Today I'll be teaching you how to multiply matrices. The contents of this video are, of course, how to multiply matrices and also a few exercises on multiplying matrices. We are going to start off with an example. Here we have two matrices. We have this first matrix, which is a 2 by 2 matrix. This means that this matrix has 2 rows and 2 columns. We are going to multiply this matrix with a second matrix. This is a 2 by 1 matrix because it has 2 rows and only 1 column. Now, how do we multiply these two matrices? Well, we are going to take a look at the first row of the first matrix as well as the first column of the second matrix. Now, in the resulting matrix, the corresponding element will be no more than the dot product of this row with this column. Now, if you don't know what a dot product is, don't worry, I'll show you. A dot product is no more than the sum of the multiplication of the corresponding elements of this row with this column. Now, this may sound like a lot, but it's not that difficult. We are going to take a look at the first element of this row, which is A. So we are going to multiply A with the first element of this column, which is E. So we have a term which is the multiplication of A by E. Now we are going to do the same for B. B is the second element of this row. So we are going to multiply B with the second element of this column, which is G. So we have a term which is the multiplication of B by G. Now, because there are no other elements left for this row or this column, we are done and we can simply add these two terms up. So the corresponding element in the resulting matrix will be A multiplied by E plus B multiplied by G. Now, you may wonder, how do I know where this corresponding element will go in the resulting matrix? Well, because we have taken the first row of this first matrix and the first column of this second matrix, in the resulting matrix this element will go in the first row and first column. So, in the upper left corner of the resulting matrix. Now, we are not done calculating this resulting matrix though, because we also have this second row left. We are going to take a look at the second row of the first matrix. We are going to take the dot product of this row with this column of the second matrix. Now, the dot product, it goes the same way. We are going to take this first element of this second row, which is C. Because this is the first element of this row, we are going to multiply this with the first element of this column, which is E. So we have C multiplied by E. We are going to do the same for D. D is the second element of this row, so we're going to multiply it with G, which is the second element of this column. So we have D multiplied by G. Again, there are no other elements left in this row or this column, so we can simply add these two terms up. Because we have taken the second row of the first matrix and the first column of the second matrix, the resulting element will be in the second row and the first column of the resulting matrix. And this element will be C multiplied by E plus D multiplied by G. Now, there are no more other combination of rows of the first matrix and columns of the second matrix left, so we are done calculating. Now, let's take a brief recap. When we are multiplying matrices, we should take the dot product of every possible combination of rows for the first matrix and columns of the second matrix. So in this example, we have two possible combinations. We have this first row in combination with this column, and we have the second row in combination with the same column. Hence, why there are only two elements in the resulting matrix. Now, let's take a look at this resulting matrix for a second. This matrix has 2 rows and 1 column, so this is a 2 by 1 matrix. It's very important to note that you can calculate the dimensions of a resulting matrix when multiplying matrices before you calculate any element of this resulting matrix. So, we just take a look at the dimensions of the matrices that we are going to multiply. We take a look at the first matrix, and we see that this matrix has 2 rows. When we take a look at the second matrix, we see that this has 1 column. So the resulting matrix will have 2 rows and 1 column. When we are multiplying matrices, the resulting matrix will always have the same number of rows as the first matrix and the same number of columns as the second matrix. Okay, let's take a look at another example. This time we are going to multiply two matrices with a little bit of bigger dimensions. We're going to take a look at the first matrix, which is a 3 by 4 matrix. So we can see that this matrix has 3 rows and 4 columns. We are going to multiply this matrix with a second matrix, and this one has 4 rows and 2 columns, so this is a 4 by 2 matrix. Now, we know how to calculate the dimensions of the resulting matrix. We just take a look at the number of rows of the first matrix, which is 3. And we take a look at the number of columns of the second matrix, which is 2. So the resulting matrix will be a 3 by 2 matrix. So this matrix will have 3 rows and 2 columns. So we have to calculate 6 elements of this matrix. Now, we are going to take a look at every possible combination of rows for this first matrix with columns of the second matrix. So let's take a look at the first row of the first matrix and the first column of the second matrix. We simply have to take the multiplication of the corresponding elements of this first row and this first column. So, as we did before, we are going to take the first element, which is A. We're going to multiply A with the first element of this column, which is M. So, A multiplied by M. Then we are going to do the same for the second element, which is B. We're going to multiply B with the second element of this column, which is P. So, we have the multiplication of B by P. We are going to do the same for the third and the fourth element. So C will be multiplied by S and D will be multiplied by V. Then we have every element of this row and this column. So we are done calculating this element and we just simply add all these terms up. So we have A multiplied by M plus B multiplied by P plus C multiplied by S plus D multiplied by V. Now, where in the resulting matrix does this element go? Well, we have taken the first row of this first matrix and the first column of this second matrix. So, in the resulting matrix, the corresponding element will be on the first row and the first column, so in the upper left corner. Now, we are going to take a look at another combination of rows and columns of these matrices that we are going to multiply. We are going to take a look at the first row of the first matrix, but now we are going to take a look at the second column of the second matrix. We are going to do the exact same. So we multiply A by N plus B by Q plus C by T plus D by W. And we take the second element. The second element will be at the first row, but the second column of the resulting matrix. So in the right upper corner of the resulting matrix. Now we have 4 other combinations left. We can take a look at the second row of this matrix with the first column of the second matrix. We're going to do the exact same thing. We multiply E by M plus F by P plus G by S plus H by V. And we have the corresponding element. Now where does this element go? Well, on the second row in the first column of the resulting matrix. So the second row, first column of the resulting matrix. Now we can take a look at all the other combinations. So we have the second row with the second column. And this will be in the second row and second column of the resulting matrix. And this will also be E multiplied by N plus F multiplied by Q plus G multiplied by T plus H multiplied by W. And we're going to do the same for the last row. The last row in combination with the first column gives us this element, which is I multiplied by M plus J multiplied by P plus K multiplied by S plus L multiplied by V. And this will go in the third row and the first column of the resulting matrix. And at last we have this row in combination with the second column. And this will give us the last element, which will go in the third row and the second column of the resulting matrix. So this is the corresponding matrix of this multiplication. Now I have another example ready for you. So this time we are going to multiply two matrices, which are both 2 by 2 matrices. So they both have 2 rows and 2 columns. Now we know that we can take a look at the first matrix and take the number of rows, which is 2. And we take a look at the second matrix and we see that this has 2 columns. So the resulting matrix will have 2 rows and 2 columns. Now we know how to multiply these matrices, we take a look at the first row of the first matrix in combination with the first column of the second matrix. We multiply A by E plus B by G, and we get the first element of the resulting matrix, which will be at the first row and the first column. Now we can take a look at this first row with the second matrix, and then we have A multiplied by F plus B multiplied by H, and this will be at the first row and the second column of the resulting matrix. We can do the same for the second row, and we take a look at the first column again. So we have the multiplication of C by E plus D by G, and this will go at the second row and the first column of the resulting matrix. And at last we have this second row with the second column, and then we have the multiplication of C by F plus D by multiplied by H, and this will go at the second row and the second column of the corresponding matrix. Now, we see that we can multiply what seems any combination of matrices, but this is not the case. There is in fact a condition. Now, to show that we can't just multiply any two matrices, we are going to take a look at this example. We have two matrices. The first one is a 2 by 2 matrix because it has 2 rows, 2 columns. The second matrix is a 3 by 2 matrix because it has 3 rows and 2 columns. Now, when we do as normal, we take a look at the first row of the first matrix and the first column of the second matrix. We are going to multiply A by E, and we can add that up with B multiplied by G. But we have no element left in this row to multiply with I. So what do we do with this last element here? I don't know. When we are taking a look at the first row of the first matrix and the second column of the second matrix, again, we can multiply A by F, we can multiply B by H, but we can't multiply any element with J, so we don't know what that term will be. And same goes for any other combination of rows and columns. We cannot calculate them properly because we have not enough elements in this row to multiply with every element in this column. So again, we don't know what this element will be. So this brings us to an important condition. We have to formulate the condition. When can we multiply particular matrices? Well, we can multiply two matrices when the number of columns of the first matrix is the same as the number of rows of the second matrix. So in this case, for example, this seems like a lot, but just let's take a look at the dimensions. The first matrix has 3 rows and 2 columns. So the number of columns of the first matrix is 2. And the second matrix has 2 rows and 4 columns, so the number of rows of the second matrix is also 2. So we can multiply these two matrices. The resulting matrix will be a 3 by 4 matrix. Okay, so now we know that when we are multiplying matrices, we should always take a look at the dimensions of the matrices that we are going to multiply. In this case, the first matrix is a 2 by 2 matrix and the second matrix is a 3 by 2 matrix. So when we take a look at the number of columns of the first matrix, we see that this is 2. So this has 2 columns. But when we take a look at the number of rows of the second matrix, we can see that it is 3. So this matrix has 3 rows. And 2 is not equal to 3, so we cannot multiply these two matrices. When you get an example like this, you should immediately know that it is impossible to multiply these two matrices. This has no outcome. Okay, now let's take a look at these two matrices. We have a 1 by 3 matrix and we multiply it with a 3 by 2 matrix. So the number of columns of the first matrix is 3. The number of rows of the second matrix is also 3. So we now know that we can easily multiply these two matrices. The resulting matrix will be a 1 by 2 matrix. Now, let's just take a look at the same matrices, but switched positions. So now the first matrix is this 3 by 2 matrix. So the number of columns of the first matrix is now 2. The number of rows of the second matrix, which is this one, is now 1. Now the number of columns of the first matrix is in this case not equal to the number of rows of the second matrix. So this multiplication is impossible. This brings us to a very important conclusion that when we multiply matrices, we can't just switch them from position. When we multiply a matrix A with a matrix B, this will not give the same result as the multiplication of B with A. So the order of matrices in a multiplication is very important. We call it that the multiplication of matrices is not commutative. Okay, we're going to take a look at a few exercises. In the first exercise, we have these two matrices with actual numbers this time. We are going to take a look first at the dimensions of these matrices to even see if they even can be multiplied with each other, and to calculate the dimension of the resulting matrix. Okay, this first matrix is a 3 by 3 matrix. It has 3 rows and 3 columns. The second matrix as well is a 3 by 3 matrix. We see that the number of columns of the first matrix is 3, and the number of rows of the second matrix is also 3. So we now know that it is possible to multiply these two matrices. The resulting matrix will be a 3 by 3 matrix. Okay, now let's get into it and multiply these two matrices. As I said before, we are going to take a look at every possible combination of rows of the first matrix with columns of the second matrix. Now let's take a look at the combination of the first row with the first column. Okay, we are going to multiply these two as usual. So this will be 7 multiplied by 1 plus 18 multiplied by 16 plus 6 multiplied by 24. And because we have taken the first row of the first matrix and the first column of the second matrix, this resulting element will be in the first row and first column of the resulting matrix, so in the upper left corner. Okay, let's take a look at the second combination. This will be with the first row and now the second column. So this element will be 7 multiplied by 12 plus 18 multiplied by 9 plus 6 multiplied by 17. And again, because we have taken the first row and the second column, now in the resulting matrix, this element will go in the first row and second column. So in this place. Okay, the other combination of the first row now with the third column will be 7 multiplied by 23 plus 18 multiplied by 6 plus 6 multiplied by 11. Because we have taken the first row and the third column, in the resulting matrix, this element will go in the first row, but now the third column. Now we can do that for any other combination. So we take a look at the second row of the first matrix with now again the first column of the second matrix. So now we have 2 multiplied by 1 plus 11 multiplied by 16 plus 8 multiplied by 24. And this will go in the second row and first column of the resulting matrix. So in the second row, first column. Okay, let's take a look at the following combination, which will be in the second row and the second column. So this will be 2 multiplied by 12 plus 11 multiplied by 9 plus 8 multiplied by 17. And because we have taken the second row and the second column, this element will go in the second row and second column of the resulting matrix, so right in the middle. The other combination with this row is with the third column. This is then 2 multiplied by 23 plus 11 multiplied by 6 plus 8 multiplied by 11. And this will go in the second row and third column of the resulting matrix. Now we take a look at the last row in combination with the first column. And this will be 14 multiplied by 1 plus 3 multiplied by 16 plus 1 multiplied by 24. And this will go in the third row, first column of the resulting matrix. The last row with the second column gives us 14 multiplied by 12 plus 3 multiplied by 9 plus 1 multiplied by 17. And this will go in the third row and second column of the resulting matrix. And then we have one last combination left, which is the combination of this third row with the third column. And this will be 14 multiplied by 23 plus 3 multiplied by 6 plus 1 multiplied by 11, and this will go in the third row and third column of the resulting matrix. Now, if everything went well, we can calculate the elements of this corresponding matrix, and then you should get this result. Now we have one exercise left. This time we are going to look at the multiplication of these two matrices. Again, the first thing you should always do is look at the dimensions to first see if it is even possible to multiply these two matrices. And if so, then you can also, again, multiply the dimensions of the resulting matrix. So you kind of know what you're looking at. Okay, let's take a look at the dimensions. This first matrix is a 2 by 3 matrix. It has 2 rows, 3 columns. The second matrix is a 3 by 3 matrix because it has 3 rows and 3 columns. So again, we take a look at the number of columns of the first matrix, which is 3. And the number of rows of the second matrix, which is also 3. So we now know that it is possible to multiply these two matrices. We also know that the resulting matrix will be a 2 by 3 matrix. Okay, again, we are going to look at every possible combination of rows of the first matrix with columns of the second matrix. So we take, again, a look at the first row of the first matrix in combination with the first column of the second matrix. And we are going to multiply as usual. So we have 0 multiplied by 10 plus minus 15 multiplied by 3 plus 7 multiplied by 0. This will go in the first row and first column of the resulting matrix because we have taken the first row of the first matrix and the first column of the second matrix. Now we are going to take a look at the first row again, but now in combination with the second column of the second matrix, and we have the multiplication of 0 by 6 plus minus 15 multiplied by minus 19 plus 7 multiplied by minus 4. This will go in the first row and second column of the resulting matrix. Again, we take a look at the first row, but now in combination with the third column, and we have 0 multiplied by minus 2 plus minus 15 multiplied by 7 plus 7 multiplied by 5. Because we have taken the first row and the third column, this element will go in the first row and third column of the resulting matrix. Then we have 3 combinations left with the second row. Now we take the second row with, for example, the first column. We multiply 5 by 10 plus 2 by 3 and plus minus 9 multiplied by 0. And this will go in the second row and first column of the resulting matrix. Again, we have the combination of the second row with now the second column, and this will be 5 multiplied by 6 plus 2 multiplied by minus 19 plus minus 9 multiplied by minus 4, and this will go in the second row, second column of the resulting matrix. Then we have one combination left, which is the second row with the third column, and this will be 5 multiplied by minus 2 plus 2 multiplied by 7 plus minus 9 multiplied by 5, and this will go in the second row and third column of the resulting matrix. Now, if everything goes well, you should get this resulting matrix. Okay guys, thank you for watching this video. If you have any questions or comments, leave them down in the section below, and I'll hope to see you in our next video.